Good morning. In this session, I am going to discuss about the surface and the groundwater resources. It will come under module 1 and it will be a part of an VTU syllabus. Let's start with the introduction. Let's see. The term hydrology is derived from the Greek word that is hydr, which means water. Logy means science. Generally, the hydrology is defined as the science of study of water is known as hydrology. Or in another way, also you can give a definition for hydrology. That is, it is the science which deals with the circulation, occurrence, and distribution of the water of the earth and earth's atmosphere is known as hydrology. So this hydrology is basically an applied science. Further, for the application point of view, it has been classified. This subject hydrology has been classified into two categories. That is, first one scientific hydrology, then second one engineering hydrology. So first one, scientific hydrology, it will involves mainly the study of academic aspects only or academic things only. But engineering hydrology will involves the study of the engineering applications. That is the estimation of water resources, then the estimation of various processes such as precipitation, evaporation, evapotranspiration and their interaction, then the study of the various problems such as floods and droughts, then strategy problem for these problems. So these are the things that will be involved in engineering hydrology. Next, if you go for, if you we'll see the hydrology cycle. So the hydrology cycle, so it's also known as water cycle. So if you see on the earth surface, the water occurs in all its three states, that is in the liquid, solid and gaseous states. Then the evaporation of water from water bodies such as oceans and lakes, and formation and movement of clouds, rain and snowfall, streamfall, and groundwater movement are some of the examples of the dynamic aspects of the water. The various aspects of water related to the earth can be explained in terms of a cycle is known as the hydrology cycle. You can see the figure here. We'll going to observe the movement of water. The starting point is ocean. Again, it will start from here, and again it will runs in the form of cyclic process. And during its momentum, during its moment of water, the various process it will going to occur. So that is, you can see the different processes. That is, example, evaporation, transpiration, precipitation, infiltration, subsurface flow, groundwater flow, deep percolation, the surface runoff, the evaporation from lakes, evaporation from vegetation. Like that, again, after this movement of water, again it will come back, again it will reaches the ocean. So it's known as complete the cyclic process. So one by one, if you are seeing the processes, so that's what we're going to discuss here. You can see, so the hydrology cycle may be divided into two major components. That is the transportation components. Second one, storage components. These transportation components nothing but the moment where you will going to observe, that is a transportation component. The storage components nothing but the water which is stored in a particular places. So first one in the transportation components, if you're saying precipitation is known as the different forms of water which will reaches the earth surface through the atmosphere is known as precipitation. So different forms of water, nothing but whether in the form of rainfall, whether in the form of snowfall, whether maybe in the form of sleet, glaze, like the different processes, different forms. Next one, evaporation. Evaporation is the one of the major moving component in the hydrology cycle. That is evaporation, nothing but the change of water from liquid state to gaseous state is known as the evaporation. Then coming to next component, third component, you can see the transpiration. Transpiration is nothing but the process of water getting lost from the vegetation or from the plant leaves. That process is known as transpiration. Next component, if you are seeing, that is an evapotranspiration. So evapotranspiration is nothing but it is one of the major process when if the evaporation is taking place from the land surface and if transpiration is taking place from the plant leaves or vegetation, both together if it is occurring at a particular time, then that process is known as evapotranspiration. The next component, if you're seeing, that is infiltration. So after the precipitation, the portion of water, it will get infiltrated, or the process of movement of water into the soil surface is known as the infiltration. Next component is runoff. Runoff nothing but the flow of water over the land surface is known as the surface runoff. Then after the infiltration, some portion of water it will run as a runoff below the earth surface and it will go into joins the streams. That is known as subsurface runoff. So these are the runoff. These are the major the transportation components what we'll go to see in the hydraulic cycle. Next one, if you are seeing the storage components. So the storage components, majorly three storage components we'll go to see in the hydraulic cycle. There is the first one, the storage in the land surface. So the water which is stored on the land surface, whether it may be in the streams, rivers, valleys, tanks, ponds, or any depressions, that is storage on the land surface. Then soil moisture storage, the portion of water which is stored, or portion of moisture which is stored in the soil, subsurface soil, that is known as soil moisture storage. Next one, groundwater storage, the water which is stored in the groundwater table, that is known as groundwater storage. That will how it will go into the groundwater, it will go into stores. That is once after the precipitation, the water it will get infiltrated. After that also some portion of water it will go into move downwards. Further it will infiltrated into the ground surface and it will go into joins the groundwater table. That once it's known as groundwater storage. So these are the major components. These major all components will play an important role in the engineering hydrology. Next one, if you see, we'll go to discuss about water balance equation. So water balance equation or a water budget equation. First, before going to discuss about water balance or water budget equation, we should know the definition of watershed. The area of land drained by a particular river system is known as the watershed or a drainage basin or a catchment area. So, what is the importance of water balance equation in the uh, hydrology or in the water resources? You can see a water balance can be established for any area of the earth surface by calculating the total precipitation input and the total various of outputs. See, the water balance equation can be applied for lakes also. It can be applied for the catchment areas also. So by that time, what we'll going to consider? So we'll majorly will going to apply this water balance equation to calculate the total precipitation input and the total and what is the total outputs from that system. The water balance approach allows an examination of the hydro cycle for any period of time. Then the purpose of the water balance is to describe the various ways in which the water supply is extended. The water balance is a method by which we can account for the hydro cycle of a specific area with emphasis on plants and soil moisture. The water balance is defined by the general hydrological equation, which is basically a statement of the law of conservation of mass as applied to the hydrological cycle. So in simplest form, so the hydrological cycle, no, the water balance equation can be applied for any catchment. That is, inflow will be equal to outflow plus change in storage. So that will be equal to finally inflow minus outflow. That must be equal to change in storage. Yes, you can see for a given catchment area, if you are applying a water balance equation for a time interval delta t, that can be expressed in this form. That is P minus R minus G minus C minus T, that will be equals to delta S, where P is your precipitation, R is your surface runoff, G will be a groundwater flow out of this catchment, E is your evaporation, T is a transpiration. Then delta S will be change in storage. This S, nothing but storage. Again, it will consist of three components. That is SS, SSM, SG, where SS will be surface water storage, SSM soil moisture storage, SG groundwater storage. So in terms of rainfall runoff relationship, the above the water budget equation can be written in this form. That will be equal to R will be equal to P minus losses, where R will be runoff, P will be precipitation, L will be losses. We'll go to solve some numericals on this water balance equation. You can see the problem. A lake has a water surface elevation of 903.2 meters above datum at the beginning of a certain month. In that month, the lake received an average inflow of 8 meters per second from the surface runoff sources. In the same period, the outflow from the lake had an average value of 8.50 meter per second. Further, in that month, the lake received a rainfall of 165 millimeters, and the evaporation of the lake surface was estimated as 75 millimeters. Write the water budget equation for the lake and calculate the water surface elevation of the lake at the end of the month. The average lake surface area can be taken as 8,000 hectares. Assume that there is no contribution to and from groundwater storage. Yeah, so here, so this is a given problem. So what you have to calculate, so you have to write the water budget equation for that lake, and you have to calculate the new water surface elevation at the end of the month. For that, the given data they given. So initially, in that lake, the water surface elevation was 903.2 meters in the beginning of the month. So after that, it will going to receive an inflow of 8 meter cube per second from the differential of surface runoff sources. The same period, we will going to observe outflow also, that is 8.0 meter cube per second. So then lake receives rainfall of 165 millimeters in that month only. Then average evaporation, it will go takes place from lake surface, that will be estimated around 75 millimeters. Then lake is having a area of catchment area of 8,000 hectares. Lake surface area will be 8,000 hectares. Now, so for a time interval delta t, the water budget equation, how we can write, this is a principal equation: inflow minus outflow volume, that will be equal to change in storage of the lake. Now first you can calculate inflow volume, what is the input parameters into the lake, then outflow volume nothing but from the lake what will be the output parameters. Just calculate that one. So that is, you can see, so I into delta t plus precipitation into catchment area will give total input volume. So q bar delta t plus evaporation into lake catchment area, again it will, lake area, it will go to give the output volume. Now one by one you can see time interval delta t. It's a 1 month in the problem itself, particularly they mentioned in a certain month. There is 1 month. So for 1 month, so just convert that 1 month into seconds. That is 34 into 24 into 60 into 60. It will give 2.592 million seconds for 1 month. Next, so inflow volume. So inflow will be, what is the inflow? You can see they particularly they mentioned inflow will be 8 meter cube per second. So 8 meter cube per second into time interval delta t, it will give 20.736 million meter cube of volume. Then outflow q bar into delta t. So outflow also they given 8.5 meter cube, sorry 8.5 meter cube per second multiplied by this time interval delta t. So you will get 22.032 million meter cube of volume. Now inflow due to precipitation. So precipitation also which is coming into the lake, that is also input. So you can consider that as an input parameter. So it will occur for an area of 8,000 hectares. So that is you have to consider here. Yeah. You can see input due to precipitation, that is a precipitation into, it will go to occurs for an area of 8,000 hectares. So for 1 hectare will be equal to 10 power 4 square meters. Convert it to hectare to square meters. So this one precipitation 165 millimeters they given, converted to meters. So after conversion, basic conversions, so precipitation into area, how much you're going to get? 13.2 million meter cube of volume in the precipitation. In the form of precipitation, it is going to enter into the lake. Then at the same time period, outflow also in the form of evaporation, it is going from the lake. So that one, if you are calculating, so evaporation, it is in 75 millimeters. They have estimated the value they given. That one converted to meters. Then again, area, so it has to be converted to hectares to square meters. So it will be, so outflow, that is the evaporation, the change of water from liquid to gaseous state. It's on one kind of loss. It will be in output only, output parameter. If you are considering that one, so 6 million meter cube, that much of outflow volume due to evaporation. Now, all values, if you're substituting in your principal here, the water budget equation, you'll go to get change in storage delta S. That is inflow volume 20.736 plus 13.2 as an inflow due to precipitation. Then outflow volume will be 22.032 plus outflow in the form of evaporation will be 6. So total will be 5.904 million meter cube of the change in storage what we're going to observe from the lake. Next, change in elevation. How are you going to calculate the change in elevation? So change in elevation can be calculated. So what is the total change in storage volume divided by catchment area if you are doing? So you are going to get 0.0738 meters. This much of elevation, change in elevation is going to observe in that lake in that month. Then new water surface elevation at the end of the month will be, so initial the water surface elevation will be 903.200 plus the change in elevation will be 0.738. So total, so if you're adding, you're going to get the new water surface elevation at the end of the month. So 903.2738 meters. So this is what is the given problem, what you need to calculate. Second, one more problem, again here we'll go to solve. You can see the catchment area of 140 square kilometers received 120 centimeter of rainfall in a year. At the outlet of the catchment, the flow in the stream draining the catchment was found to have an average rate of, that is first one 1.5 meter cube per second for the first 3 months, 2 meter cube per second for the 6 month, and 3.5 meter cube per second for the remaining 3 months. There is an output volume. So what is the runoff coefficient of the catchment? You have to calculate. Then if the afforestation of the catchment reduces runoff coefficient to 0.35, what is the increase in the abstraction from the precipitation due to infiltration, evaporation, transpiration for the same annual rainfall of 120 centimeters? So first, what you need to calculate? So you have to calculate what is the runoff coefficient. Then if the afforestation, because of afforestation, the catchment reduces to the runoff coefficient to 0.35. So by that time, what is the increase in abstraction from the precipitation or due to infiltration, evaporation, transpiration for the same annual rainfall? So here, so before afforestation, so just what is the volume, input volume, and what is the coefficient by considering what is the runoff coefficient, you just calculate. So time period will be, I'll consider, they mentioned, you can see in a 1 year, in a year. So 1 year delta T, I'm going to consider input volume to the catchment through precipitation. So its area of catchment 140 square kilometers. So precipitation will be rainfall 120 centimeters. Now volume into I, that is VI, it will represent input volume, that will be equal to 140 into 10 power 6, that is 1 kilometer square will be equal to 10 power 6 square meters. So it's in terms of centimeters. If you want to convert to centimeters to meters, divided by 100 divided, so same thing, basic conversions. Now input volume will be 168 million meter cube input. The output volume, that will be equal to, so output volume for 3 time periods they given. For starting 3 months, it will be 1.5 meter cube, 1.5 meter cube per second. Then for the second remaining 6 months, for the middle 6 months, it will be 2 meter cube. Then for remaining 3 months, it will be 3.5 meter cube per second. Now total it will be 27 million meter cube per month. But we have to convert that one. So total it will be total runoff output volume what you have to calculate. So 27 for all per month we got 27 million meter cube per month. Now for the 1 year it will be 365 days. That is a 12 years for 12 months. Now you can see here 12 months. Now that has to be converted to again seconds. So it will be 70.956 million meter cube. Then the runoff quotient will be 70.956 divided by the total input volume, that will be 4.42 is the runoff quotient. Then abstraction volume, so 168.0 minus the runoff quotient, this output volume, how much you got, that is a 70.956. If you're substituting here, 97.044 million meter cube of, that is an abstraction volume, what you're going to get. Now after that, second case, after afforestation, so you can see the runoff quotient, that is a 0.35 multiplied by the total input volume, that is 168, you will going to get so 58.8 million meter cubes. Now new abstraction volume will be 168 input volume minus a year, so total after afforestation. So by considering runoff quotient 0.35, how much you got? 58.8. So how much you're going to get? 168.0 minus 58.8, 109.2 million meter cube of new abstraction volume you're going to get. Then increase in abstraction volume will be this 109.2 minus the inch previous before afforestation. So abstraction volume, how much we got? 97.700, 97.044. Now 109.2 minus 97.044, how much you going to get? 12.156 million meter cube is the increase in abstraction volume because of after afforestation. So that's it, some problems. Thank you.